Okay. Right. So yeah, this is under supervision of David Leslie, Henry Moss, Ed, and Lachlan. So the system of interest, the objects that we're interested in this talk is ocean currents. And one example of some particular region where we care about ocean currents is the Gulf of Mexico. Well, this is the Gulf of Mexico, unless you're in the States. So we want to zoom in on this part. So this top bit is the Deepwater Horizon oil rig. So it's near Louisiana and Mississippi, and it's basically this huge infrastructure that constantly digs up oil from the floor of the seabed. And as these things go, it spilled, and it broke down at some point, and that caused a major problem. So in April 2010, we have this oil spill, and it causes catastrophic things like death of animals and pollutions in the ocean and ecosystem. So in this type of particular setting, we are quite interested in studying the ocean currents to understand how widespread, how fast, and how far they could go with the spills. And there are many other scenarios where we're interested in ocean currents as well. But this type of cases are really important for us to work on. So by ocean currents and by modeling ocean currents, what I really mean is that we want to create something like this. So we have a particular region, and we want to have this sort of vector field on a sort of fine enough grid, and we want to know how things are moving at different times. And this will tell us, for example, if I have a oil spill here, we can use this vector field as some sort of ODE system to learn at a further time, say 5 days later, where this small drop of oil will be reached. Obviously, there are also climate and sort of meteorological applications. For example, we can use that to understand how would a storm or how would temperature changes affect inside this Gulf of Mexico, in fact, affect other parts of the world. But ultimately, we want some vector field like this plot here. So how are we going to get our data? So currently, there are two quite regularly used methods. One is this mooring buoy, which is something that you drop into the ocean and you put this is moored to the ground, so it doesn't really move spatially that much. And it's every, say, 5 minutes, 1 minute, is going to give you a reading on the temperature, the vector of ocean currents at that point. You'll send it to the satellite and it will be received. And on the right is another commonly used tool, which is a drifter. And what a drifter is this type of sensor that you can throw into the ocean. It will just follow the ocean flow and it will just go. And every few minutes, you're going to take a reading and send to the satellite and back to ground. So relatively, a fixed buoy is going to cost quite a lot more, like hundreds to 1,000 times more than a drifter. So financially, it is quite favorable to think about drifters, and this is what we're going to be looking at in this talk. So what are people currently do with these drifters? So they basically throw them all over the world. So on the left, you can see this global drifter program, which is a American-driven program where they put these drifters across the world, get the data, and then put it as an open source platform where everyone can go and take a look at the data and do stuff with it. But also we have, this is the WA waves, so Western Australia waves, where people basically do similar things, but with slightly different objective in mind. But all they do is they manage to put some drifters, and then they can track it, and they put it in dashboards, and people can look it up online. So yeah. And there are a lot of open data sets and papers about these drifter data sets. So this is quite an important paper, quite relatively new. So it's 2021 by Johnson Lilly and Paula Brunias, where they consolidated about 25 years worth of drifter data, and they put it into this open source package, and people can look it up. Right, so all these are good. So why are we interested in these things, right? So if we look closely into this paper that I just mentioned, they have about 20 sets of experiments over 2 decades. And one set of experiment, they will place some drifters, let it flow, and get some data out of it, and they will stop. And we have another experiment, put more drifters, and in so on and so forth. And in this particular case, this is this splash investigation. Basically, what they did is they put all these drifters closely packed in this point and let it go. And you can see that they have very similar trajectories, right? And if we are interested in the ocean currents of the entire Gulf, you can see that this covers only a very tiny portion of it. So this is not very good if our objective is the coverage, right? Maybe it's good for some other purpose, but let's say we are only interested in the coverage. We want to understand the entire Gulf as good as possible. Then this is an undesirable placement, right? And there are other experiments inside this paper that does similar things, but they are slightly more spread out. And you can see they manage to get a better coverage of the space, right? And then there's this example where things are more spread out at a different location, and you can see they cover a much larger portion of the Gulf. So the goal of this really is about this point. So all data are informative, sure, but some data are more informative than others. And that comes to the key goal of experimental design, was to how do we make observations with a limited budget. So we only have budget to do 5 observations. Where should we look to get the maximum amount of information out from them? And yeah. So there are existing ways where people do this type of experimental design. They are model agnostic and model based. So model agnostic means that they don't really worry too much about the particular system and particular question they're interested in. They kind of just do a uniform approach. So yeah, so the first approach is random. So they just close their eyes and put it somewhere and then just hope it works. But we can do something smarter. We can do a space filling approach. So where we segment the space into different portions and we try to look at each of these portions sort of evenly. So the hope is to cover the big space at a more uniform way. And of course, they are model based. And what I meant by ad hoc here is that they talk to some oceanographers, and the oceanographer will tell you, hey, you probably want to put it at these 5 locations because oceanographically they mean something and they will lead to a good result. And people will just follow these suggestions and do them, which is great, but it's not it's quite reliant on expert knowledge, and sometimes it's good to have other ways as well, which is active learning's approach. And this approach is on using existing data to guide our future observations. So sequential experimental design or active learning follows this way. So we have this big cloud of all the potential places we can observe, we can look, and we have a subset of it being our current data. So we know something. We don't know everything, but we know something. And there's a lot that we could explore. First, we use our existing data to fit a model. And then, based on the model, we will have some level of uncertainties or some quality that can tell us how each of these potential observations will be valued. So we have a way to score all the potential observations from our current model. And then we'll look at all these different scores and pick a good place to look. And we'll look at, we'll observe, and we'll add that to our current data sets, and we'll go through this loop again. So this is why it's called sequential experiment design, because we're doing this full loop of actions over and over again until our budget runs out, or until we have obtained enough or good enough data about our system. And more concretely, this update model part will be using a Gaussian process regression for its computational ease and its way that can give us a lot of uncertainty measures about different locations. And then we will come up with nice acquisition functions to tell us how good a potential observation location is, subject to our current knowledge. Any questions so far? Good. Right. So I'll briefly mention this, what a Gaussian process is, but I think this will be quite straightforward for this audience. So let's assume we have a multivariate Gaussian distribution. We draw a sample from it. This multivariate Gaussian is centered, so it has zero mean, and it somewhat correlates across dimensions. And we are going to display the different dimensions horizontally. So now I have just shown you one point, this one dot here. So it's the first dimension of this draw. We have two more, the second and third dimension. They are highly correlated, so you can see they're very similar. I have more points and more points and more points. So this is a 30-dimensional Gaussian. We take one draw and then we basically horizontally display it. And you can see this looks somewhat like a function that is quite smooth. And this is basically one of the motivations of using a Gaussian process to model a function of interest. And it allows quite a bit of flexibility. So formally, a GP, a Gaussian process, is a stochastic process indexed by X that's equipped with a main function that tells you the average behavior and a covariance function that tells you about, for two different points, how is the relationship between how closely related and how correlated they are. So yeah, so we specify two things. We have specified the main function, we specify the covariance function. And usually the main is set to 0 for simplicity a lot of the cases. And the key choice that we are going to make is on choosing this covariance function, also called a kernel. So this kernel choice is quite important. So for example, we can use this squared exponential kernel, which is extremely smooth. That gives you these type of nice functions. So these are possible draws from this GP. And we can use something that's rougher, a turn kernel, for example. And this new parameter just indicates how differentiable it is. So if it's new 1/2 is 1 time differentiable, and if it's 3/2 is 2 time differentiable. Or it could be, yeah. So it tells you how differentiable this process is. So each draw is a function, and with SE, it's infinitely differentiable, so it's smooth. And with this pattern, they are finally differentiable. So depending on the context and what you're trying to model, you want to choose different kernels to basically reflect your prior knowledge about the system. And then you can do regression. So what it really means is that you have a prior being a GP. So this particular function that you're interested in, you say, okay, prior is a GP with particular mean, particular covariance. We make some observation, we have a likelihood, and we update the prior with the likelihood to get a posterior. So in this case, when we assume we make exact observations or noiseless observations, we have basically a very good recovery of the truth and some nice uncertainty bounds around it. So these green bits are the two standard deviation error bound, uncertainty bounds. And if you assume there's some noise, it does quite well as well. And you can see the general structure has been preserved and learned, basically. But this is not what we are interested in. We are interested in learning modeling a vector field. And all I've shown you so far is about a scalar quantity. So how do we go from scalar to vector field? So what a vector field is really two components, right? A 2D vector field has two components. It's u and v, so x direction velocity and y direction velocity. We just put two Gaussian process on them. And the dependency is the interesting bit. So if we assume they are independent, so we ignore the correlation between u and v, then we get one approach. So it's the velocity decomposition. So basically, we can just assume that whatever happened in the x direction of the velocity has nothing to do with the y direction velocity. So we just treat the big problem into two sub-problems and do them separately. But that's obviously not a good idea because these vector fields, u and v, are definitely correlated in some way. So what we'll do is we'll do some sort of transformation to decompose this vector field into components that are more likely to be independent. And then we impose two GPs on them. And this transformation is conducted using this Helmholtz decomposition from the vector calculus literature and fluid dynamics. So what this Helmholtz decomposition does is that for a vector field in 2 dimensions, we can break it down into a gradient-free part and a rotation-free part. So a rotation is sort of like a swell kind of behavior where things are going cyclically, and the gradient is some sort of blowing up or contraction. And this is basically a fact from mathematics that tells us that in the two-dimensional case, we can break any vector fields down into these two components. And obviously, it's not a unique decomposition. In three-dimensional, things are slightly more tricky, but in two-dimensional, it is fine. And what we do is that instead of placing a GP on the U and V, we place them on the gradient part and the rotation part. And because gradient and rotation are linear operators, we can combine them in this overall kernel or the vector field. And you can see that this K helm is the overall kernel for the vector field. And you can see that they have all entries in this covariant structure, including off-diagonal ones. So there are correlations being modeled here. So this is not really a new model. People have been studying it in oceanography and machine learning. The important takeaway is that it's a nice way to model a vector field. It can model the divergence and curl separately. So that is often of interest in a lot of the applications, well, because they are interested in different, very special properties about these currents. And because of this GP setup, we can assume Gaussian observations, and then give us conjugate posterior. Right. And also, this Gaussian process allows us to have very nice uncertainty quantification. So at a particular point, we can check our GP and says, okay, tell me how uncertain you are about this point's value. And then based on the covariance function, we can know that quantity explicitly. So these are all very nice properties about the GP and why people like to use them in our setting. And this vector field is a draw from this Helmholtz kernel. And it looks convincingly enough to most people that this is a sensible enough vector field. And obviously, we can do regression. So the picture in blue is a ground truth that I took from some open data set. And I take some observations from it. So these red arrows are observations. And basically what we can do is we can do this GP regression, use this conjugate posterior, and we can turn out the graph on the right. So the green arrows are the posterior predictions of the vector field. And there are some circles. I'm not sure if you can see them clearly, but there are some circles around telling you how uncertain you are about that particular point. And you can see that these two vector fields are quite close in terms of a lot of the structures. For example, this big swirl here that is being learned, and also a lot of these directions. And this is implemented using a GPJAX, which is an open source package in Python. And so it works quite well. So the final thing that I want to mention here before I move on to the active learning is about our data. So I mentioned just now we have two options of observing. One is mooring, which is more expensive, and the other is a drifter, which is much cheaper. And here we are looking at drifters. And I also told you that how people do this. So these drifters are being placed in the ocean, and they will flow according to the ocean currents, and they will pick up signal along the way. So you can see in this graph, if we have some underlying vector field and we start the drifter from some point, it's just going to follow this vector field precisely up to some noise, and then it's going to tell you about the observations. So here is very interesting because spatially, this drifter is moving, and the motion is determined by the vector field. But it's precisely those vector field that we're trying to learn. So there's a very closely connected things, right? So we want to learn the vector field from these drifters, and the drifters are dictated by the vector field. So it makes the problem more interesting, and it just gets dark. All right, great. Is this fine? Right enough? Okay. Yeah, this is taking too much energy apparently. Any questions before I move on? Yeah.
Do you actually put in the GPs on the stream function and the natural?
Correct. Yes.
Do you have some understanding of how smooth you expect those functions to be?
Yeah, it's a very good question. So in the pictures and all the experiments I will show you later, I'm using a squared exponential. In reality, you want to use something that is more rough. So you want to use a Merton 5.2, for example, because of yes. So yeah, so because you can look at the spectral properties and then you go and match with what people have done in oceanography, and the conclusions usually is SE kernels, so square exponential is way too smooth. Merton 5.2-ish is good enough. So there's this paper that basically describes this. I can point you to it if you're interested. But yeah, so there are people who study these drifter trajectories exclusively, and basically the conclusion is that Merton is usually good enough. Yeah. Yes.
Follow-up question. In the ground truth data, there's some vectors specifically that point in the opposite direction. Line of kind of, I guess you whatever.
Are they? Well, I think that has more to do with the scale of the vector, so they kind of collide. And in this left-hand side, this particular data set, grid, is averaged over 100 kilometers times 100 kilometers.
I guess my ultimate point is that there's often opposite currents like crash against each other.
Mhm.
This would be a point of discuss. So how do you justify using continuous, like sort of a kernel that GP that makes the somewhat not like maybe
One point is if you look at it at fine enough resolution, they should be continuous. If you average them out over a larger, so if you do a very coarse resolution, then yes, it will be a problem. So, but obviously the resolution that you're going to use is subject to your computational budget, subject to how good your observations are, right? Because there's different. So far in this particular data set and the several data sets I have been looking at, is not a major issue. But yeah, it could happen, and especially if you look at it far enough. Yeah. Yes.
And just on the decomposition.
Yeah.
Because those two functions aren't smooth, is that ever pose non-identifiability problem?
Always.
Sorry?
Always.
Always.
Well, in a sense that, I mean, in a lot of the GP literature, it's kind of swept under the carpet, right? This identifiability issue. And my sort of defense in our setting is that we are not interested only in modeling the ocean currents, but to that's not good. Okay, let's come here. That's weird. Sorry. Yeah. So my defense in our setting is that modeling is not our sole objective, but doing this sequential experimental design is the true objective. So once we get better data through our sequential experimental design, we can then take those data, use a much better, much more accurate model, and do proper analysis that has less these GP restrictions. Because there are people who do, like a proper PDE-driven, huge numerical model, and then they do some sort of, like I forgot the name, like statistical FEM, this type of approaches where they do inverse problems to. Oh, it's back. Inverse problem to them. That will be a much better way to resolve what you have just described about the identifiability issues. But in our setting, because GP is very nice in the properties of uncertainty quantification, it's quick, it's intuitive, we are quite happy to work with them for now. But obviously, yes, so we could try to use a much more accurate and much more realistic model. But that will also require us to make this model able to produce uncertainty quantification and quick to update. One promising potential solution is the deep network of deep adaptive designs by people like Tom Ringvos and their group, and some people in the Aalto University, where they try to train a neural network to do this adaptive design policy stuff. And that's because they're using amortization and neural network training. At deployment, when they actually place these drifters, it's instant. They might spend a lot of time training these policies, but in the end, when they use them, it's quick. But in our case, because we want to do a real-time deployment, this GP stuff is, right. That will be context dependent. And this one, I haven't looked into them, but there are things we can consider when, especially when we look at a very particular application for a very small region or for a very precise application. Then yeah, these are things we should and we probably will look at if we do this very precise application as a general methodology now. Yeah. Yes. Yeah, so it's a multi-output, vector output GP. Yeah, because the correlation here is yes. It's not as intuitive for our oceanography perspective, and the quality is not as good. It was so this precise problem. Yeah, this precise problem was basically studied in this paper. That's basically they argue for using their approach over this, say, velocity composition, and yet they do impose some correlation there to the MC approach. But yeah, so this is they argue that in this type of context where ocean currents and vector fields are involved, their method is more desirable. Yeah. Yes.
One more quick question.
Of course.
Yeah. So essentially, I think okay, when modeling the correlation between the drag part and the rotation, rotational part.
Here we assume they're independent.
Oh, okay. Yeah, because I was about to ask that. Okay.
We probably shouldn't if we are being honest to ourselves.
Yeah.
For now, we are assuming them, but at some point, yeah, we'll impose some dependency structure there.
Yeah, because the question is saying that, okay, does the choice of dependence you impose depend on your choice of functions that you pick? Anyways.
So, okay, so I'll probably should explain this a bit more. So here we have just a potential function and stream function, and we give them basically two GP prior on them, and they are specified by two separate kernels. Here I'm using SE kernel for both, and they are independent between these two functions. But we can use different kernels here, like maternal that we just discussed, and we can impose a dependency structure here between the two things as well. And we can recover something like this. I've written it in one of the notes I've written, so I can show you if you want. But basically, it will be quite straightforward, and it will involve minimum adjustment to everything if we impose some dependency structure here. And realistically, they should be dependent. Yeah. Even though it's hard to argue statistically what is the best dependency or what is the most realistic dependency, but some form of dependency is probably needed. Right, I'll move on. Let's come to this active learning and the new stuff that I studied in this piece of work. So let's just recap on what this Bayesian active learning is. So it's the sequential experiment design. So in the Bayesian framework, we have this base rule, we have pi, we have the likelihood, and we get a posterior, subject to this normalizing constant and whatnot. What this really means is that we have some current belief of the system, of the parameter, we have some new data, and we update our belief based on that. And the question of active learning in this Bayesian setting is that how should we pick this new data point that maximize the gap between the updated belief or the current belief or the posterior and the prior. So we have this big brackets of all the potential observations that we can look at. We have a existing model G, we have some existing data D, and we have some utility function U that basically tells us about what are the things that we want to aim for to achieve from this whole approach. So for example, in this active learning setting, we are mostly interested in learning the whole system. But if you are doing Bayesian optimization, for example, we are only interested in the maximizer or the minimizer of the function. So depending on which task you're trying to perform with this type of framework, you'll pick a different utility functions. And even within active learning, you can pick different utility functions as well. And then you get this end result of this equation. So you have this utility that takes into account of a particular observation location, your current model, your current data, and you take the expectations of this predictive, so this potential observations predicted observation, right? So you have, like, let's say we observe at some location and we have our GP model and we look at the predicted mean of that point. That gives us a predictive distribution, right? And then we try to run this computation across all the possible observation locations, and we'll give a score to each of them. I will pick the maximizer as our next observation point. This is basically what we're doing with Bayesian active learning. So how should we pick this utility? Right? This utility should reflect the quality of the potential observation with respect to our goal. So if our goal is to learn this unknown function, maximize our information for this active learning, we can do things like maximum variance. So we have say we have a GP and we have different points, and we say that, okay, at each point, what's the variance? Okay? And we'll just look at the point that has the largest variance. Or we can do maximum integrated variance, which is slightly smarter. So we say that, okay, we have a GP, we have some data for each point. Assume we observe at some particular new point, we refit our GP with that new potential observation. How will the total variance change before and after making that hypothesized observation? And we do that across all the potential observation points, and then we compare from there. So let's implement them here. So, okay, nice. So the left-hand side is some synthetic ground truth. It's just some vector field that we know. So we draw. So the left-hand side is a draw from this Helmholtz kernel. So we know its parameters. And the right-hand side, we assume that we make these drifter observations. So we start with an arbitrary uniformly drawn location. Then we have, okay, so at this point, we have one trajectory of drifters, about 5-8 points, and we fit a GP posterior to it. So you can see that around this region is very purple, so it means it has a low standard deviation. We know quite well. And everywhere else is yellow, so we have high uncertainty about them. So here we are using the maximum variance policy. So we are going to look at one of the yellow points, basically, because we know very little about them. Okay, we drop another drifter. The old drifter is still moving. We drop another drifter, more drifter, more drifter, more drifter. And as you can see, slowly, we are making better observations, right? But this is real quirk about this maximum variance policy is that because of how this GP is set up, we are always looking at a fixed, closed domain. The variance is always highest around the boundaries. So it's always going to look at the boundaries, but these boundaries are not very interesting. So this maximum integrated variance where we look at the gap between making the observations and before and after making the observation. So that makes it more interesting. So as this GIF will show, you are going to do a slightly better job. Well, actually a much better job in this case, where we are making, much better predictions. You can see from these mean squared error and average standard deviation that you're doing quite well with recovering the ground truth. But if you actually think and pause and look at this utility choice, we are only looking so far at placing and considering the initial point of placement. Right? We are going through only one X instead of the whole trajectory that we're going to observe. And we just say that, okay, if we only make one observation, where are we going to place it to get us the most information? And this makes it quite myopic. especially in our setting where the observations are as trajectory instead of a point. And this is something that we want to resolve. Therefore, we propose ballast, which is a way to resolve this issue. So we want a policy that first incorporates future observations. So instead of looking at the initial point, we want to look at a few points that is going to be. Number two, you should respect the drifted trajectory structure. So it can't be just the standard non-myopic stuff people do in the experimental design literature, where they can make any combinations of observations. It must be following the physics of a drifted trajectory. So it must be, like this line trajectory thing. And also we want to make it computationally feasible, so we can implement it in real time. So what we propose and we try to do is this ballast idea is that we are only going to consider initial position still, but we're going to construct this thing called look ahead. Basically, it says that if I put it here, where it might go, right? And this where it might go can be learned or can be predicted or hypothesized using our GP model, right? Because the drifter is following the vector field, and we have a model for the vector field from our surrogate model, which is the GP stuff, right? So we can use the GP to make a prediction about where the point might be, and we can compute the utility using these several points instead of just one point. So if you look at this formula, we can see it's basically the same with minor adjustment. So previously, this chunk is just one x, it's one initial location. But here we have this p delta t x f hat. So this is the constructed look ahead. So what it says is that starting from initial location x, we have some hypothesized vector field f that we assume the ocean current is. It's an approximation, it's a hypothesis. It's not a ground truth. And we do basically ODE solver for time t at step size delta, right? Because we can treat our vector field as some sort of ODE, right? We can do this like Euler discretization. We say one point, we look at the gradients, we move, and then we look at the gradient, we move, we look at the gradient, we move. And this will give us a trajectory instead of a point. And we incorporate all these points into this utility function. So basically what we do is we'll just add them up. We have a whole trajectory of 5 points. We just look at the utility of the first, second, third, and I just add them up. I will take the expectation and I will do the argmax. Okay? So everything else is the same except for this constructed look ahead. And that's the novelty here. So most of these things are quite straightforward. So this discretization, this ODE solver, we can just use Euler method. The step size, we can just pick some suitable t, like it could be like 5 time steps. It's quite arbitrary in our setting because we don't want it to be too long, because that will give a computational cost. That's not realistic and whatnot. And the step size must be small enough so it's realistic. But all these are fine. But the main problem is how do we approximate the field, right? So the first approach is we can just use the predictive mean of our surrogate model. But this is not a good idea because initially, when we have very few data, it's just going to be a lot of zeros because our prior mean is 0, or whatever our primary mean is. Okay? And also, it doesn't really follow a vector field because the mean is not following a vector field. Our draw from the GP follows a vector field. So we can... Sam, you look confused. Is it fine?
No, it's fine.
Okay. We can do this sample average. So instead of using the posterior mean, we take a draw from this Helmholtz GP. We use that as one possibility of what the truth might be. We run this, we get the utility, we save it. We take another draw of the vector field. We compute the same thing, and then we just keep doing it for k times, and then we just average them out. Right? So intuitively, you can think about this ballast as where we're taking the sample average as a Monte Carlo approximation of doing a stochastic integral over the entire vector field, right? So we are basically integrating this f hat out, but instead of doing this actual computation, we do this Monte Carlo approximation. So for example, the yellow points are the current observations here. And we look at a few points. So in reality, we look at all these grid points, and here we just pick 3. And we take, say here I put around 10 draws. So 10 draws from this posterior vector field, and then we generate 10 trajectories. So in this middle part, because we have high certainty about our posterior, about our vector field, these trajectories barely vary because we have high certainty. So all these draws are very similar. But in the regions where we have low certainty, these trajectories are very different, which is basically what we expect them to do. So you can see that these points will yield a low uncertainty and a low score consequently, and these high uncertainty. So this is the point, in fact, that we pick. So we pick here, and then we basically query the ground truth, and then we give us these observations, and then we just keep repeating doing this. Yeah. So coming back to our this framework. So where we have potential observations, some current data, updates, acquisition, come back, observe, update. We have some current data. We fit a GP regression. We consider this acquisition, and this heat map just basically tells us about the score that we get this BALLAST stuff for. And you can see this cross is the point that has the highest score. So that is the point we're going to look next. And we come back, we do everything again. And it's a GIF that does what I just said, but in dynamic motions. So we did some basic simulations, and okay, so because of time, I'm going to skip most of them. Basically, we have better performance than doing nothing. Like, so doing this type of ballast and active learning stuff is better than space filling approach or random approach. And 2 important observations, they're observations only, is that number 1, we can pick any utility to pair with ballast, right? Because what ballast really is this projection that we're doing and this simulation that we're doing, right? So we can pair this with any base utility. It could be this max variance, max integrated variance. It can be information gain. It could be anything. And we argue and we observe that doing ballast in this type of setting is uniformly going to improve regardless of the base utility. Of course, if you pick a very good base utility, the improvements margin might not be huge because you're already doing something very sensible already. But if you do something that is very naive, like max variance, just by including this ballast in, you can outperform a much smarter, much more costly base utility. Okay? So this is 2 observations that we made. And in terms of computational cost, ballast is not that costly, and it can be quite easily parallelized. If you are in Python and JAX, you can just use VMAP, and somehow it works. Yeah, so this is quite a preliminary study, and there are lots to be investigated. We can conduct more experiments to think about what are the other base utilities that we pick and match it with ballast and see how these things go. We can do things like risk averse, so we penalize uncertainty or prefer uncertainty, and then some information theoretic ways. I have a derivation about expected information gain, because in our setting, we have a GP surrogate model and EIG. Usually it's not tractable, but here it's extremely tractable. And basically, we can write this thing down explicitly. I have a blog post on this, but it's quite cool. You can just use one trick and it just works out. And yeah, of course, we are also interested in being time varying. So our vector field so far is always static. But that's not realistic for ocean because ocean moves and it changes over time. So active attempt that I'm trying to make is to extend everything we have discussed so far to time varying. But it makes the active learning more interesting because we can't change the past. So we can't just place a drifter in, that's like 2 days ago. We have to always look forward, right? So that imposed some really interesting things with our active learning. And of course, there are things we can do with, this cost of drifter, right? Because some guy has to drive a boat into the middle of the ocean, place it. So you don't really want them to travel too far or place them too far apart, or else it's not very feasible, right? And for example, in one of the application, people who actually place these drifters, they will usually ask some other guy who already are planning to go somewhere, say that, hey, mate, come on, I pay you some money, you drop the drifter for me along the way. So you have a fixed trajectory of the boat's movement. You are just going to say that at time point A, B, C, we place a drifter. So that narrows down the region that we're going to search for in our active learning. Instead of the whole ocean, we have one line and then a few points from the line. So these all makes the problem much more complicated and much more interesting, of course. And if you're interested in more, this is a workshop paper in Europe last December, and you can find this thing on this link there. And thanks.